Hi, everybody. I really wish I was there. Unfortunately, Viper has me pinned down here at Ames this week, and I won't be able to fly there and back in time. So I'm giving this remote. Hopefully, I'll be able to see you all at League, though, sooner than later. This the abstract was more about science measurements and our key observations, but given the session title, I turned this into more of a mission update. I think most of you have heard of Viper or have heard of its predecessor, Resource Prospector. We've been kind of working on this, we being a large group of people. Many of you have been working on this idea for 10 plus years. Viper is really a dual community mission in that it serves both the science and exploration communities equally. The upper right-hand corner here shows our level 1 mission goals as written down from our level 1 requirements documents, characterize the distribution and state of lunar polar volatiles, of water, and other volatiles, cold traps and regolith, and provide the data necessary to evaluate ISRU. So it's got a broad range of observations that it will be conducting, and I'll get into that in a bit here towards the end. Where we're at right now is back in June, we passed our KDP-D, which is a formal gate review that enters you into phase D, or flight system integration. We had already begun flight system integration several months prior to this gate review, but you still need to do the gate review. It went well, unanimous pass, and we're chugging along. We're now less than 1 year from rover delivery robotic for integration onto their Griffin lander. So the launch is on the horizon. Nominal launch is November 10th, 2024, with currently a 5-month mission duration. Looking at ways that we might be able to extend that out a month or two beyond that. So really get into the details of the traverse planning, as you'll see in a second here. The science instruments, this is the Viper toolbox. There are 3 prospecting instruments that are on continuously while roving. There is a neutron spectrometer system. Rick Elphick is the PI. It measures both epithermal and thermal neutrons. You can see it sticking off the nose of the rover here. We have the near-infrared spectrometer system, which is a near-infrared spectrometer that runs from 1300 to 4000 nanometers. It has a 4-channel thermal radiometer for measuring temperatures and other compositions. It provides some composition information. It has a 4-megapixel camera system with 7 color LEDs for doing high resolution context imaging and composition. I'm the PI of that instrument. Then we have the mass spectrometer observing lunar operations instrument, or MSOLO. This is a mass spectrometer that runs from 0 to 100 AMU. Typically, we only run it up to 70, however, while prospecting. Janine Captain at Kennedy Space Center is the PI of that. It's also part of the Prime 1 mission, which is going on into the Machines 2 that Ben just talked about. And then also part of the Prime 1 mission is the Trident drill, which is a 1 meter percussive auger drill that will sample in 10 centimeter bites down to 1 meter depth. We also have a lot of cameras. Can't drive a rover without cameras, at least this rover. And these cameras were engineering cameras. They were navigation, hazard, et cetera cameras. We said, well, wait a minute, let's turn those into science instruments themselves. So we've worked with the team to do extra calibration, work them into the science planning, not just navigating. And so that's now called the Visible Imaging System, or VIS. And Ross Beyer is the science PI for that. And then we also are using the Rover Inertial Measurement Unit as a science instrument. This is a really cool idea that Kevin Lewis has demonstrated with the Mars 2020 IMU. We are actually flying the Mars 2020 flight spare IMU, so it's very appropriate, I think. But this will allow us to do subsurface sounding, gravitometry while we're roving. But even more cool is doing seismic sounding when we're drilling. That will actually allow us to sense down to maybe 3 or 4 meters down to water concentrations in the percent level. So we've extended, by using the IMU, we've extended our vision into the subsurface for water ice and just other geologic context, down from a meter with the neutron spectrometer down to several meters with the IMU. Where we're at, we are in the middle of systems INT. The rover is going to be approximately done this October, fully built and getting into environmental testing. I now just have some show and tell photos of some of the flight hardware coming together. You see a proud Papa with his flight wheel modules there on the left. The rover is being built integrated down at Johnson Space Center, I should mention. On the right here, you have the lower chassis. And if for those of you, I know many of you have seen the mock-up, full-scale mock-up of the rover. If you haven't, there's one at Ames, one at Johnson. Try to see it. PowerPoint slides don't give the size of the rover justice. It's a large rover with the mass being about 2.5 meters tall. This is the lower chassis. Here's a lower frame of the chassis that comes up and around where these solar panels are attached. Here's the flight mast and gimbal assembly. So this is what stands on the top of the rover. You see two cameras here and two lighting systems. It uses stereo navigation to create hazard maps and allow waypoint driving for the rover drivers. Because it goes into dark places, it is the first rover with headlights to go into PSRs. And down below that, you see the flight nav light checkout. The lights are LEDs with a center wavelength of 460 nanometers. So it has a beautiful blue tint. The color was determined after a lot of testing in the Lunar Lab, which is survey run here at NASA Ames, looking at various colors and determining the best contrast for lowest power required lighting system. On the right, you see bracket MLI closeout for the Nervous instrument. So this is down in the belly pan now. And the previous, you saw the lower chassis. The belly pan is part of that chassis. It's looking down below the rover. Here you see the two apertures for the camera and the near-infrared spectrometer. I'm sorry, the light. It's got a near-infrared light and the near-infrared spectrometer. Here's the camera, the 4-channel radiometer, all tucked away and wrapped up tightly. And then M-Solo harness closeout is being shown here. Actually, I believe it is today that M-Solo was integrated onto the chassis right next to Nervous. And I heard this morning that went very well. So now both M-Solo and Nervous flight instruments are integrated into the rover. NSS comes later. The rover's like an onion, where the things in the middle have to be integrated first and everything then comes after. NSS is on the outside. It comes a little bit later. So soon drill will go in there, batteries, etc. And then finally NSS solar panels and so on. Here's a really fun video showing rover testing at the Glenn Research Center Slope Lab. This is on a 30-degree slope. We do not intend to drive on 30-degree slopes. But they test the rover well beyond its planned capabilities to ascertain exactly what it can do and what it can't do. The rover mobility system is unlike anything we've flown to another planetary body before, in that it is a 4-wheel independent suspension driven. And so each wheel can operate independently, and being able to do so, we can get ourselves out of embedding. For example, we deliberately embedded ourselves there, but then we can do this fun little walk with just the rear wheels. We can do it with all 4 wheels if needed to actually dig ourselves out of a hole. This allows us to do crab driving, point turning, lots of maneuverability. For scale, the wheels here are 50 centimeter diameter wheels. And this is just a McGrew. This is a test bed that's meant to match the overall mass of the rover when it would be, how it would be on the moon. So our mapping approach and overall science planning concept, often you'll hear in the popular press, so Viper will find water. And I want to say, very clearly, we are not saying we are going to find water. We are going to do a methodical mapping of a range of thermal environments and geological settings to build the correlations between volatiles, and including water, and a range of environmental parameters. That's what we can really sign up to do and actually verify that we can and will do. We are going to a place where there is enhanced hydrogen, and there's, I personally have no doubt we will see water in some form or another. It's just a matter of the concentrations. We are sensitive down to, tens to hundreds of parts ppm. So we're sensitive enough to see even the smallest amounts. However, more importantly is to get these correlations. I see VIPER as a cornerstone providing critical information for future missions to actually really focus and go take the next steps in terms of exploring these environments and at the poles of the moon. So the way we've organized our operations into these 4 thermal regimes or ice stability regions. And I've been talking about these since Resource Prospector, so you all probably know about them. They're defined as where the ice is expected to be stable on the surface. And this comes from modeling that Matt Siegler and his team do. And that allows us to actually plan. So we're not just, well, where are we driving? Well, we have these various ice stability regions we identified. We have a set of requirements at level 2 and level 1 to map these environments. And that's what these traverses are being planned to do. This is a strategic traverse. This is our baseline. It says it's an example. This is our actual baseline traverse. It may change, but this is what we're working to now. It might be hard to see, but there's little blocks here. It's gray ones, yellow ones, green ones, yellow ones, green ones. These are science stations of the various ISR types. This is a superficial ISR. The red and the green is shallow, yellow is deep, and gray is dry. We land here, Griffin Lander places us here, and we drive when we explore each one of these PSRs over. This is a 4 lunar day mission. We've planned the 5th lunar day and we're looking at a 6th and 7th. But in this 4 lunar days, we're driving approximately 30 kilometers, including up to 2 kilometers inside permanent shadow regions. And that, I should be clear, that permanent shadow region is not just a permanent shadow region. It is a region where it's predicted that ice is stable at the surface. As you all know, they're not one and the same. And in particular, this very old degraded PSR, this one's estimated by the VIPER science team to be about 3.7 billion years old, is largely not stable on this side at the surface. Temperatures are warm because of scattered light on these steep slopes. So we actually come in on this side and actually explore the area where water is expected to be stable. So that's the strategic plan. Where we're at now is going from the strategic to the tactical planning. And
we're going to need you to wrap up pretty soon, Tony.
This is like my last slide. We go from strategic planning to the tactical, where we're going from large scale planning that's done in an automated way to involving the entire science team to really plan to 1 meter data products, the actual plan we will be driving. So over the next several months, we're planning the 1st lunar day. I won't read through all of these. This is up here for you guys to look through. But we actually use what we call the Lunar Dynamic Science Table. It's a living STM, if you will, that evolves and changes with the mission to actually plan the observations that we do. We do real-time science. We do real reactive science on the surface of the moon. So we're building the tools and the processes that we can adapt as we learn quickly, adapt quickly as we learn to maximize the science that we get out of VIPER. And with that, thank you.